Welcome to Ultimate Sleep Doctor. Tonight, we'll be gently exploring a question that's echoed through the ages. Where does time go when it passes? It's a mystery woven into the fabric of our existence, a dance between perception and reality. Scientists study this phenomenon through the lens of relativity and memory, revealing how our experience of time is remarkably fluid. Perhaps it's not vanishing, but transforming, layering moments into a vast, shimmering tapestry. Let's acknowledge the quiet comfort of simply being, recognizing that all things change and return. Consider the feeling of a favorite memory, the way it still holds a potent warmth. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift. Let's begin. Let's consider a question that has puzzled thinkers for centuries. Where does time go when it passes? It's a remarkably subtle mystery, one that isn't about clocks or calendars, but about the fundamental nature of reality itself. The feeling that time moves forward, that a moment becomes a memory and a seed sprouts into a tree, is deeply ingrained in our experience. But what governs this unidirectional flow? The most compelling scientific explanation centers on a concept called the arrow of time, inextricably linked to the laws of thermodynamics and a principle called entropy. At its core, the arrow of time describes the observation that time appears to move in one direction, from past to future, while remaining fundamentally the same regardless of which direction we observe it from. We remember the past, but we cannot remember the future. We can observe a broken vase shattering, but we never see the pieces spontaneously reassemble themselves. These asymmetries, these directional tendencies, are what define the arrow. Now let's delve into the heart of this asymmetry: entropy. Entropy, in simple terms, is a measure of disorder or randomness within a system. It's a hugely important concept in physics, and its relationship to the arrow of time is truly remarkable. The second law of thermodynamics states, quite simply, that in a closed system, one that doesn't exchange energy or matter with its surroundings, entropy always increases over time. Think about a perfectly ordered room. You spend time cleaning, arranging furniture, and putting everything in its right place. That's a state of low entropy, a highly ordered, organized state. However, left to itself, without any intervention, the room will gradually become messier. Clothes will get tossed on the floor, books will pile up, dust will accumulate. It's a natural tendency towards disorder. This is because there are countless more ways for things to be disordered than there are for them to be ordered. The universe itself began in a state of incredibly low entropy, a state of near-perfect order, shortly after the Big Bang. This initial state was extraordinarily concentrated. All the energy and matter were packed into a tiny, incredibly hot and incredibly dense space. Since then, the universe has been expanding and evolving, and this expansion has driven the increase in entropy. Every process we observe, from a burning log to a star's nuclear fusion, inevitably increases the overall entropy of the universe. When wood burns, it releases heat and light, and the organized chemical bonds of the wood are broken down into simpler, more disordered forms: ash, smoke, and gases. The energy is dispersed, becoming less concentrated, less useful in terms of doing work. It's transformed into a state of higher entropy. Consider a cup of hot coffee placed in a cold room. Heat flows from the coffee to the room, increasing the entropy of the room and decreasing the entropy of the coffee. The coffee cools down, becoming less ordered, while the room warms up, becoming more disordered. This process is irreversible because it's fundamentally driven by the increase in entropy. You can't spontaneously get the heat back from the room and put it back into the coffee. The key thing to understand is that the universe isn't just passively increasing entropy. It's actively defining the direction of time. The fact that entropy always increases gives us a direction for time. We perceive the past as the state of lower entropy and the future as the state of higher entropy. It's not that time itself is flowing, but rather that the universe is evolving according to the rules dictated by thermodynamics, rules that fundamentally favor increasing disorder. The arrow of time is, therefore, not a force pulling time forward, but a consequence of the universe's inherent tendency towards greater randomness. Scientists have conducted experiments to probe this connection even further. One famous experiment involved dropping grains of sand through a glass of water. The sand always fell to the bottom, creating a distinct pattern. If you were to film this process in reverse, attempting to make the sand spontaneously rise and reassemble itself, it would be an unbelievably improbable event, requiring a decrease in entropy, something that has never been observed occurring spontaneously in a closed system. This experiment brilliantly demonstrates the connection between the arrow of time and the second law of thermodynamics. The universe doesn't allow time to move forward. It is the direction in which entropy increases, and that increase defines our experience of time's flow. Furthermore, even seemingly reversible processes, like mixing cream into coffee, eventually lead to a state of maximum disorder. While you can initially mix the cream and coffee, the resulting mixture is far more disordered than the separate states. It's impossible to spontaneously unmix the cream back into its original state. The concept of entropy and the arrow of time aren't just abstract scientific ideas. They have profound implications for how we understand the universe and our place within it. It suggests that the past is fixed, while the future remains open, constantly evolving towards a state of ever-increasing disorder. As the universe continues to expand and evolve, driven by this relentless increase in entropy, the flow of time, and our experience of it, will continue its unidirectional journey from a state of low disorder to a state of maximum disorder, forever shaping the reality we perceive. The universe, in its magnificent sprawl, doesn't operate on a simple ticking clock. It's far more nuanced, far more fluid. For centuries, people believed time was this constant, unwavering river flowing equally in all directions, regardless of where you were or what you were doing. Then, in the early 20th century, a brilliant German physicist named Albert Einstein completely shifted our perspective with his theories of relativity. These weren't just ideas. They were revolutionary discoveries that fundamentally altered our understanding of space and time, revealing a startling connection between the two. Einstein's work started with two key concepts: special relativity and general relativity. Let's begin with special relativity, which deals with the relationship between space and time when objects are moving at constant speeds. Einstein's core postulate of special relativity is quite simple, yet profoundly unsettling. It states that the laws of physics are the same for all observers in uniform motion. What does uniform motion mean? It means moving at a constant speed in a straight line. Now, imagine you're sitting perfectly still on a train that's traveling at a steady pace. You could easily conduct an experiment, toss a ball in the air, measure its trajectory. Everything would seem perfectly normal. But what if someone else is standing outside the train watching you? They would see the ball moving in a curved path because it's moving both horizontally, with you on the train, and vertically, upwards as you throw it. Both of you are observing the same physics, but you're seeing different effects because you are in different states of motion. This difference in perspective leads to one of the most astonishing predictions of special relativity. Time is relative. It's not absolute. The faster you move through space, the slower you move through time, relative to someone who is moving slower. This isn't a trick of perception. It's a fundamental property of the universe. Let's consider a thought experiment. Imagine a spaceship traveling at an incredibly high speed, close to the speed of light, the fastest speed anything can travel in the universe. Inside the spaceship, there's a clock that works by bouncing a beam of light between two mirrors. Each bounce represents a tick of the clock. Now, an observer on Earth watches this spaceship whizzing by. Because the spaceship is moving so fast, the light beam inside the spaceship appears to be traveling diagonally. It's covering a longer distance than if the spaceship were stationary. Since the speed of light is constant for all observers, regardless of their own motion, something has to give. And what gives is time itself. From the Earth observer's point of view, time is passing slower for the people on the spaceship. The clock on the spaceship appears to tick more slowly than a clock on Earth. It's not that the people on the spaceship are aging more slowly. It's that time itself is stretched out for them. This effect is known as time dilation. The faster the spaceship moves, the more pronounced the time dilation becomes. If the spaceship were to travel at the speed of light, which, thankfully, is impossible for anything with mass, time would, theoretically, stop completely for the astronauts relative to an observer on Earth. Now let's move on to general relativity, which builds upon special relativity and introduces gravity into the equation. Einstein realized that gravity isn't just a force pulling things down, it's a curvature of spacetime itself. Think of spacetime as a giant fabric, a four-dimensional grid combining the three dimensions of space, length, width, and height, with time as the fourth dimension. Massive objects like planets and stars warp this fabric, creating a dip or curve. Other objects then follow the curves in spacetime, which we perceive as gravity. So what does this have to do with time dilation again? Well, the stronger the gravitational field, the greater the curvature of spacetime, and the slower time passes. This means that time passes slightly slower at sea level than it does on top of a mountain, because you're closer to the Earth's mass, and therefore experiencing a stronger gravitational field. The effect is tiny, but it's measurable with incredibly precise atomic clocks. It's been demonstrated by placing atomic clocks at different altitudes and confirming the difference in their ticking rates. Near incredibly massive objects like black holes, where gravity is unbelievably strong, time dilation becomes extreme. Time would pass incredibly slowly for an observer near a black hole relative to someone far away. The implications of Einstein's theories are profound. They show that time isn't a fixed, universal constant, but rather a dynamic component of the universe, interwoven with space and affected by motion and gravity. It's a concept that challenges our intuitive understanding of reality. While these effects might seem abstract, they have real-world applications. For example, GPS satellites orbiting the Earth experience both special and general relativistic time dilation. Because they are moving at high speeds and are in a weaker gravitational field than we are on the surface, their clocks tick slightly faster. Engineers have to account for this time difference to ensure that GPS systems work accurately. It's a remarkable example of how Einstein's theories, initially considered bizarre, have become essential to our everyday technology. Ultimately, Einstein's work demonstrated a universe far more complex and beautiful than anyone had previously imagined. A universe where time itself is not a simple, unwavering river, but a flowing, curving current, influenced by the very fabric of space and the immense power of gravity. The universe, as we've explored, possesses a certain directional pull, a relentless march forward dictated by the laws of thermodynamics. But time isn't just a cosmic river flowing uniformly. It's deeply intertwined with how we, as conscious beings, experience it. Our perception of time isn't a direct readout of the universe's ticking clock. Instead, it's a remarkably flexible and often quite bizarre phenomenon, constructed primarily within our own minds. It's a landscape sculpted by emotion, attention, and memory, creating vastly different experiences for different individuals, and even for the same individual at different times. Consider the simple act of waiting. 5 minutes can feel like an eternity if you're anxiously anticipating a phone call. Conversely, an hour spent engrossed in a captivating book can vanish in what seems like a blink. This variability isn't random. It's governed by a complex interplay of psychological factors. The brain doesn't simply record the passage of seconds and minutes. It actively creates a narrative of time, assembling fragments of experience into a coherent sequence. A crucial element in this construction is attention. When we're fully absorbed in an activity, playing a musical instrument, engaging in a complex conversation, or meticulously crafting something, we tend to experience time as moving much faster. This is because our brains are dedicating a large amount of processing power to the task at hand, effectively filtering out the passage of time. The neural pathways associated with the activity become highly stimulated, and the brain doesn't have the resources to constantly monitor and register the intervals between events. It's as though the system is prioritizing the immediate experience over tracking the abstract concept of time passing. Conversely, when we're bored or waiting for something to happen, our attention is scattered. We're constantly anticipating, analyzing, and ruminating, which actively prolongs our subjective experience of time. The brain, Sensing this lack of engagement amplifies the sensation of duration. This heightened awareness of time's passage makes it feel like it's dragging on. The neural networks associated with boredom tend to be less active, leading to a feeling of extended time. Memory plays an equally significant role. Our recollections of past events aren't perfect recordings. They're reconstructions, shaped by our current emotions, beliefs, and biases. The emotional intensity of an experience dramatically influences how we perceive its duration. Vivid, emotionally charged memories tend to be associated with longer perceived durations, whereas emotionally muted events seem to disappear quickly. A joyful childhood memory, brimming with excitement and laughter, will likely feel longer in retrospect than a routine, unremarkable afternoon. Furthermore, the way we segment time, the way we divide it into discrete units, can also impact our perception. We typically organize our experiences into seconds, minutes, hours, and so on, but these are just arbitrary divisions. The brain, however, isn't rigidly bound by these units. It's more likely to judge the duration of an event based on the number of significant events that occurred during it. A day filled with numerous memorable moments will feel longer than a day with only a few significant occurrences, even if the actual time elapsed is the same. The brain employs a remarkable chunking mechanism, grouping related pieces of information to simplify cognitive processing. This process also influences our sense of time. When we're actively processing information, we're breaking down the flow of experience into smaller, manageable units, which can create the illusion of faster passage. However, if this chunking process is disrupted, for example, if our attention is constantly being pulled in different directions, it can lead to a distorted sense of time. Interestingly, the experience of time is not uniform across the brain. Different regions specialize in processing different aspects of temporal information. The cerebellum, for instance, is heavily involved in timing motor movements, while the prefrontal cortex plays a crucial role in episodic memory and the subjective experience of time. These areas communicate and interact, but their relative contributions can shift depending on the context and the nature of the event being experienced. Neurological research, utilizing techniques like fMRI, functional magnetic resonance imaging, has begun to unravel some of these complex processes. Scientists can observe which brain regions become active during tasks that manipulate our perception of time. These studies consistently demonstrate the dynamic and multifaceted nature of temporal processing, reinforcing the idea that time is not simply a physical phenomenon, but a profoundly psychological one. It's a construction, constantly being rebuilt and reinterpreted within the framework of our own consciousness. The phenomenon is also influenced by age. As we get older, our perception of time tends to accelerate. This is thought to be related to changes in the brain's ability to encode and retrieve episodic memories. With age, the richness and detail of our memories often diminish, leading to a subjective compression of time. The brain, perhaps sensing this decline, might compensate by accelerating the rate at which it perceives time passing. Ultimately, the subjective experience of time is a testament to the incredible adaptability and complexity of the human brain. It highlights how our perception of the world is not a passive reflection of reality, but an active, creative process. It's a fascinating reminder that even something as fundamental as the passage of time is, in large part, a story we tell ourselves. The universe, as we've explored, doesn't experience time in the same way we do. It's a concept deeply interwoven with gravity, speed, and, surprisingly, life itself. A fundamental and incredibly consistent process governing countless living things, from the smallest bacteria to the largest whales, is built around something called a circadian rhythm. These rhythms aren't conscious decisions. They're ingrained, automatic cycles dictated by internal mechanisms. They represent a profound connection between an organism's physiology and the predictable changes in the environment, primarily the daily cycle of light and darkness. At the core of a circadian rhythm lies a biological clock, a complex system of genes and proteins that act like a master conductor, orchestrating a symphony of changes within the body. These clocks aren't found in one specific location, but rather distributed across various tissues, with the most prominent one residing in a tiny area of the brain called the suprachiasmatic nucleus, or SCN. The SCN, nestled just above the optic nerve, acts as a central timekeeper, receiving direct signals from the eyes. When light enters your eyes, a specialized retinal ganglion cell, intrinsically photosensitive retinal ganglion cells, IPRGC, specifically transmits information about light intensity and duration to the SCN. This triggers a cascade of biochemical reactions, resetting the clock and initiating a cycle. The SCN then sends signals out to almost every organ system in the body. These signals aren't electrical impulses in the same way a nerve transmits information. Instead, they're hormonal signals, primarily melatonin. Melatonin is a hormone produced by the pineal gland, another structure in the brain, and its production is profoundly influenced by the SCN. During periods of darkness, melatonin levels rise, inducing feelings of drowsiness and preparing the body for sleep. As light increases, melatonin production decreases, promoting wakefulness and alertness. This interplay between light and melatonin is the most recognizable aspect of a circadian rhythm. However, the influence of the SCN extends far beyond simply regulating sleep-wake cycles. It governs a vast array of physiological processes. For example, the timing of digestive activity, when you feel hungry or full, is significantly influenced by the circadian clock. Food intake is typically highest during periods of peak alertness and activity, aligning with the daylight hours. Similarly, the body's metabolic rate, the rate at which it burns calories, fluctuates throughout the day, again under the control of the circadian rhythm. The internal biological clock also impacts hormone production. Cortisol, the stress hormone, follows a daily pattern, rising in the morning to prepare the body for activity, and then declining in the evening. The reproductive systems of many animals, including humans, are also governed by circadian rhythms, with hormone levels changing predictably throughout the 24-hour cycle. Importantly, circadian rhythms aren't solely determined by external light cues. While light is the strongest synchronizer, the body possesses an inherent, roughly 24-hour cycle. This means that even if you were to spend your entire life in complete darkness, the clock would still continue to run, though its accuracy would eventually drift slightly. This drift is due to subtle variations in the length of the cycle, often referred to as free running. The exact length of a free-running cycle varies between individuals and species, reflecting differences in their adaptation to their natural environments. For instance, creatures with nocturnal lifestyles typically have cycles that are closer to 24 hours, while diurnal species, those active during the day, have cycles that are slightly longer. Researchers have identified numerous clock genes that are repeatedly switched on and off in a rhythmic pattern, which are central to the operation of the biological clock. These genes, such as purr, cry, and clock, form intricate feedback loops that control the production of melatonin and other hormones. The stability of these loops is what allows the biological clock to maintain its precision over extended periods. It's fascinating to consider how these rhythms have evolved. The existence of circadian rhythms likely arose because it conferred a significant survival advantage: the ability to anticipate and adapt to predictable changes in the environment. Animals that could align their activity patterns with the daily cycle of light and darkness were better able to forage, avoid predators, and conserve energy. Furthermore, the remarkable robustness of these rhythms is a testament to their importance. Even under conditions of significant disruption, like jet lag or shift work, the biological clock attempts to realign itself, demonstrating its powerful influence on the fundamental processes that sustain life. Studying these rhythms offers invaluable insights into the workings of living organisms and highlights the remarkable connection between time and life itself. The investigation into biological clocks continues to unlock the mysteries of human health and behavior. Disruptions to circadian rhythms, through things like irregular sleep patterns, exposure to artificial light at night, or working at odd hours, have been linked to a wide range of health problems, including obesity, diabetes, depression, and cardiovascular disease. Understanding and respecting the power of the biological clock is therefore increasingly recognized as a crucial component of promoting overall well-being. The universe, as we've explored, isn't a simple, linear progression. Time isn't just a river flowing steadily forward. It's woven into the very fabric of reality, and some of the most perplexing aspects of quantum mechanics hint at connections between this fabric and what we perceive as temporal experience. Let's delve into quantum entanglement, a phenomenon so bizarre it seems to defy our common-sense understanding of space and time. Quantum entanglement occurs when two or more particles become linked in such a way that they share the same fate, no matter how far apart they are. It's as if they're communicating instantaneously, which initially baffled even Albert Einstein, who famously called it spooky action at a distance. Consider a pair of photons, particles of light, created together. These photons aren't just similar, they're intrinsically connected. One might have a vertical polarization, and the other, instantaneously, will also have that same polarization, even if they're separated by vast distances across a lab, across a city, or across the galaxy. The crucial thing is that before we measure the polarization of either photon, it exists in a state of probabilistic superposition, meaning it's potentially both vertically and horizontally polarized simultaneously. It's only upon measurement that it chooses a definite state. Now, the really strange part is that this instantaneous correlation isn't due to some hidden signal traveling between the particles. It's not like one photon is sending a message to the other saying, "I'm vertically polarized, so you be vertically polarized too." Instead, the act of measuring one particle immediately defines the state of the other. This happens faster than the speed of light, which initially seemed to violate Einstein's theory of special relativity, which states that nothing can travel faster than light. However, and this is a critical point, entanglement doesn't allow for the transmission of information faster than light. We can't use entangled particles to send a coded message instantaneously. While we know the state of the second particle immediately after observing the first, we can't control what state the first particle will choose when we measure it. The measurement outcome is random. It's the correlation itself that's remarkable, not the ability to manipulate it for communication. But what if this instantaneous correlation, this quantum link, has a deeper connection to our perception of time? Some physicists theorize that entanglement might be a fundamental way the universe handles temporal relationships. They've proposed models suggesting that entangled particles aren't simply correlated across space, but rather across time. The idea, still largely theoretical, is that entangled particles might be linked through a shared temporal dimension. Think about it this way. Our experience of time is built upon the accumulation of moments, each distinct yet connected to the last. We remember the past, we live in the present, and we anticipate the future. But what if the now isn't a fixed point, but rather a zone of interconnectedness where past, present, and future are subtly intertwined? Entanglement, with its instantaneous correlation, could provide a mechanism for this connection. One particularly intriguing concept arises from research into quantum time crystals. These are structures, often involving entangled atoms, that exhibit periodic behavior in time. They oscillate without dissipating energy, a phenomenon that violates classical physics. Some scientists believe that studying these time crystals might offer insights into how temporal correlations could be sustained and how they relate to the broader structure of space-time. The existence of time crystals suggests that time, at the quantum level, isn't necessarily a unidirectional flow. Furthermore, research into quantum teleportation, not the beaming up people from Star Trek kind, but rather the transfer of quantum information, highlights the perplexing link between entanglement and the no-cloning theorem. This theorem states that it's impossible to create an identical copy of an unknown quantum state. Instead, when you transfer the quantum state of one particle to another through entanglement, the original particle's state is destroyed. It's as if the information is instantaneously reconstructed at the destination, bypassing the need to physically transmit the information. The implications are profound. If quantum entanglement demonstrates a connection that transcends spatial distance and potentially time itself, It raises questions about the nature of causality. Does the future influence the past, or vice versa, through these entangled connections? While we don't have definitive answers, the ongoing exploration of quantum entanglement is forcing us to reconsider our most fundamental assumptions about time, space, and the very nature of reality. It's a reminder that the universe is full of surprises, and that even the most deeply ingrained scientific theories can be challenged by the seemingly paradoxical behavior of the quantum world. The universe, it seems, isn't just a linear progression. It's a beautifully complex web of interconnectedness, where time and space are interwoven in ways we are only beginning to understand. The universe, as we experience it, feels incredibly linear. We move from one moment to the next, a constant flow of cause and effect, a river carrying us relentlessly forward. But what if this feeling of linear time is just a trick of our perception? What if, instead of flowing, time exists as a vast, static landscape, much like space itself? This is the core idea behind the block universe theory, a concept that challenges our fundamental understanding of reality. It proposes that all moments, past, present, and future, are equally real and exist simultaneously, arranged like slices in a gigantic, four-dimensional loaf. The origins of this theory lie in the mathematical framework of Einstein's theory of relativity. Special relativity, with its insistence on the relativity of space and time, revealed that time isn't an absolute, unchanging backdrop against which events unfold. Instead, time is interwoven with space, forming a single continuum known as spacetime. Massive objects warp this spacetime fabric, and this warping is what we perceive as gravity. But the implications of relativity extend far beyond just gravity. It suggests that time's passage isn't uniform across the universe. Time slows down for objects moving at high speeds relative to a stationary observer, and time also slows down in stronger gravitational fields. The block universe theory takes this a step further. If spacetime is malleable and relative, it follows that the flow of time we perceive is an illusion generated by our own limited perspective. Just as an airplane moving across the Earth's surface doesn't actually change the shape of the Earth, but simply creates a different slice of it for the observer, we, as observers within our local patch of spacetime, are simply experiencing a particular slice of the four-dimensional block. Consider a train traveling at a constant speed. To someone standing still outside the train appears to be moving, changing its position in space relative to the surrounding landscape. However, to someone inside the train, everything appears perfectly still. They are in their own unchanging frame of reference. The block universe theory suggests we're like passengers on this cosmic train, perceiving only a limited segment of the track, a specific block of spacetime. The mathematical language used to describe the block universe is called Minkowski spacetime. This spacetime is represented by four coordinates, three spatial dimensions: length, width, height, and one temporal dimension: time. Instead of thinking of a point in space x, y, z, we think of a point in spacetime x, y, z, t. This t represents not just a duration, but a specific moment in the complete block. Every event, every action, every thought exists as a coordinate within this four-dimensional structure. It's crucial to understand that within the block universe, the past and future are not merely unknown. They are just as real as the present. The past is gone. It exists as a fully formed block, just as distant galaxies exist. Similarly, the future isn't a blank slate. It's already there, waiting to be observed by our present-day selves. This doesn't necessarily imply that we can travel through time in the way depicted in science fiction. Instead, it suggests that all possibilities, all potential timelines, are already laid out within the block. Think of a vast, intricate tapestry. Each thread represents a moment in time, and the entire tapestry is fixed and complete, regardless of whether anyone is looking at a particular section. We, as observers, are simply moving along the tapestry, tracing a line through the threads. Our experience creates the illusion of movement, while the tapestry itself remains perfectly still. The block universe theory has profound implications for concepts like free will. If all moments in time already exist, then our choices may seem predetermined. However, proponents of the theory argue that this doesn't negate free will. It simply means that our choices are part of the block, woven into the fabric of space-time. Our subjective experience of making a decision still plays a crucial role. We feel like we're choosing, and that feeling is itself a component of the block. Furthermore, the block universe theory offers a compelling solution to the time travel paradoxes that often plague science fiction. The classic grandfather paradox. If you travel back in time and kill your own grandfather, preventing your own birth becomes less of a problem. Within the block universe, there are potentially multiple versions of you, existing within different blocks of space-time. If you were to interact with a past version of yourself, you wouldn't be changing your own timeline, but rather creating a branching timeline or a parallel universe. Of course, the block universe theory remains a complex and debated topic in physics and philosophy. It's a challenging concept to grasp, and it raises many questions about the nature of reality, consciousness, and our place in the universe. But it's a theory rooted in solid mathematical foundations and offers a radical, yet elegant, perspective on the most fundamental aspect of our existence, time itself. It invites us to consider that perhaps the universe isn't a river flowing towards a future, but a vast, timeless landscape, and we are simply explorers, moving through its intricate dimensions. The question of where time goes when it passes isn't simply about its relentless march forward. It's deeply intertwined with something far more perplexing: the undeniable influence the past exerts upon the future. If time were just a river, flowing steadily onward, carrying everything along with it, then change would be a chaotic, unpredictable event. But the universe, as we've begun to understand it, doesn't quite operate that way. There's a persistent, underlying connection, a subtle but profound feedback loop between moments. Consider a simple example: a domino effect. When the first domino falls, it sets off a chain reaction, predictably influencing the fall of every subsequent domino. However, the dominoes aren't just passively responding to the initial push. They carry within them the memory of the impact. The energy transferred during the first fall isn't simply lost. It's redistributed, altering the trajectory of the later ones. This isn't merely a mechanical system. It's a demonstration of how an event, once enacted, leaves a measurable, discernible footprint on subsequent events. This principle extends far beyond the realm of falling blocks. Consider the behavior of a billiard ball after a collision. The angle at which it strikes another ball, the energy imparted, and the resulting spin. All of these are determined not just by the initial impact, but by the accumulated history of collisions that have preceded it. The table itself, the friction of the felt, the precise angle of the shot, these are all variables contributing to the ongoing cascade of events. But what if we move from the macroscopic to the microscopic? The behavior of subatomic particles introduces a layer of complexity that challenges our intuition. Experiments involving quantum mechanics have repeatedly shown that the past state of a particle can actually influence its future behavior. This isn't about some mystical force. It's rooted in the concept of quantum entanglement. Two entangled particles, regardless of the distance separating them, share a fundamental connection. When a measurement is made on one particle, the state of the other instantaneously changes, seemingly violating the speed of light. The implications of this aren't always obvious, and interpreting them is a complex undertaking. However, the consistent observation of these correlations suggests that the past state of one particle is somehow encoded within the other, affecting its subsequent properties. It's as if the universe remembers the delicate dance of these particles, maintaining a connection that transcends spatial separation. Now, let's delve into the peculiar idea of retrocausality, the notion that a future event can influence a past one. This doesn't mean time travel in the traditional sense, of course. It's more nuanced. Research in areas like nonlinear optics has demonstrated that light can be affected by its own past electromagnetic fields. A pulse of light, when exposed to a returning electromagnetic field, can alter its own phase, effectively remembering the earlier pulse and changing its behavior. The crucial element here is the measurement. The act of observing, of making a measurement, appears to be a fundamental process that introduces this feedback loop. It's as if the act of gaining knowledge about the past alters the past, creating a self-consistent, evolving system. This doesn't necessarily imply that you could go back in time and change an event. Instead, it suggests that the future, our knowledge of it, is inextricably linked to the present. Think about a complex system like a weather pattern. The present weather isn't solely determined by initial conditions. It's influenced by the ever-changing atmospheric dynamics, which are themselves shaped by past events. A slight shift in temperature, a change in wind patterns, these can be traced back to prior events, creating a chain of cause and effect that extends far into the past. Furthermore, consider the role of information. Every interaction, every exchange of energy creates a record, a disturbance in the fabric of space-time itself. This record, while potentially faint, persists and can be detected and interpreted. The more complex a system is, the more intricate this record becomes, and the greater the potential for future events to be influenced by the past. The universe, it appears, isn't simply recording events, it's actively processing them. The past isn't a static archive, It's a dynamic element that continuously shapes the present and, consequently, the future. It's a feedback system operating at every level of reality, from the smallest quantum particles to the largest cosmological structures. This raises profound questions about the nature of reality and determinism. If the future can influence the past, does that mean that everything is predetermined? Or does the universe embrace a more complex, self-organizing process, constantly adapting and evolving based on the interplay of past, present, and future? The answers, as always, remain elusive, a subject of ongoing scientific inquiry and philosophical debate. It's a humbling reminder that our understanding of time, its flow, its direction, its very existence is far from complete. The human experience of time isn't a universal clock ticking at the same rate for everyone. This fundamental truth, often overlooked in our scientific explorations, is beautifully revealed when we look at how different cultures throughout history have understood and organized their relationship with time. Anthropologists and historians have uncovered a stunning diversity of temporal frameworks, suggesting that time, at least as we feel it, is a construct shaped by societal needs, religious beliefs, and the rhythms of the natural world. Ancient civilizations, for example, rarely conceived of time as a linear progression, marching steadily from a definite past through a present into a predetermined future. The Mesopotamians, builders of the first complex societies, understood time as cyclical. Their calendar, based on the movements of the sun and moon, was deeply interwoven with religious beliefs about the eternal return of the gods and the seasons. Each year was not just a sequence of days. It represented a complete cosmic drama, a rebirth and renewal mirroring the annual flooding of the Tigris and Euphrates rivers, a source of both devastation and fertility. Their concept of Mu-S letter 1E2B a serpentine deity, epitomized this cyclical understanding, embodying both destruction and the promise of rebirth. Moving eastward, the ancient Egyptians possessed a similarly complex and interwoven temporal worldview. The annual flooding of the Nile was the cornerstone of their existence, dictating agricultural practices and, consequently, their entire social and religious life. Time was perceived through the succession of these floods, each represented by a specific god in the pantheon. The concept of Ma'at, truth, justice, and cosmic order, was inextricably linked to the annual inundation, highlighting the importance of maintaining balance and harmony within the cyclical flow of the river, and by extension, within the cosmos. The meticulous record-keeping of the Egyptians, including the creation of pyramids and elaborate tombs, wasn't simply a practical necessity. It was a deliberate attempt to anchor their lives within this grand, repeating cycle. Contrast this with the Polynesian cultures, particularly the Maori of New Zealand, where time was understood through a system known as Mataranga, which encompasses a holistic perception of the universe and its interconnectedness. Time wasn't a measurable commodity, but rather a woven tapestry, or wa, encompassing the past, present, and future, all existing simultaneously. Ancestral spirits weren't merely figures from the past. They actively participated in the wa, influencing events and advising those who could listen. The concept of udu, balance and reciprocity, served as a framework for navigating this interconnected temporal landscape. Actions in the present had immediate and often profound repercussions within the Wa, demanding careful consideration of consequences and a deep respect for the spiritual realm. As societies moved into more centralized states, particularly in Europe, the linear, progressive view of time began to gain traction, largely due to the influence of Judeo-Christian theology. The creation narrative, with its distinct beginning, middle, and end, solidified the idea of time as a divinely ordained sequence. This framework facilitated the development of historical narratives, allowing for the categorization of events and the attribution of meaning to the past. The Roman concept of tempus, often translated as time, initially carried this linear connotation, emphasizing the importance of chronological order and the legacy of imperial power. However, even within Europe, variations persisted. Celtic cultures, for example, held a more fluid understanding of time, closely linked to the rhythms of nature and the cycles of the seasons. The Druids, keepers of Celtic knowledge, emphasized the interconnectedness of past, present, and future, and their rituals were designed to align individuals with the natural world and the spiritual realm. The concept of fairy time, a realm existing alongside human time, further complicated the linear perception. Further complicating the picture, indigenous cultures across the Americas developed intricate systems of temporal understanding. The Hopi of North America, for instance, believed that time wasn't a river flowing in one direction, but rather a spiral, constantly turning back on itself. This reflected their deep connection to the land and their awareness of the repeating patterns of nature. The concept of kawa, the inherent spirit of things, underscored the belief that everything possessed a history and a destiny, woven into the fabric of time. Similarly, the Inuit cultures of the Arctic possessed a nuanced understanding of time, intimately tied to the movements of animals and the changing seasons. Their calendar wasn't based on abstract divisions, but on observable phenomena, reinforcing a deep-seated awareness of the cyclical nature of existence. The diversity of these cultural perspectives highlights a crucial point. Our modern, scientific conception of time as a uniform, measurable entity is a relatively recent development. It's a construct that has emerged alongside industrialization, technological advancements, and a particular way of understanding the world, one that prioritizes efficiency, progress, and control. Recognizing the multitude of ways in which other cultures have perceived time offers not just a fascinating historical perspective, but also a profound reminder of the subjective and culturally shaped nature of our own experience. It challenges us to consider whether our own linear understanding is simply one possible framework, and encourages us to explore the myriad ways in which time can be felt, understood, and ultimately lived. The shimmering tapestry of time, as we've begun to understand it, isn't a uniform, objective river flowing steadily from past to future. Instead, it's woven with threads of experience, and a remarkably significant portion of that weaving is carried out by our memories. It's a fascinating and somewhat unsettling truth. Our conscious feeling of time's passage isn't a measurement of objective duration, but rather a construction built upon the solidity of what we remember. This construction is deeply tied to the emotional weight of those memories and the way they interact within our brains. Consider the experience of a long, monotonous train journey. If the journey is filled with uneventful scenery and quiet contemplation, it likely feels remarkably short. Conversely, if you're trapped in a conversation with someone you dislike, or perhaps grappling with anxieties, the journey can stretch into an interminable expanse. The difference isn't simply the physical distance covered by the train. It's the density of remembered moments, the good, the bad, and the simply noticeable, that dictates your subjective experience. Neurological research has revealed a strong connection between the hippocampus, a small but vital seahorse-shaped structure in the brain, and our ability to form episodic memories, memories of specific events, tied to a particular time and place. The hippocampus isn't just a passive recorder. It actively reconstructs these memories each time we recall them. And this reconstruction isn't a perfect copy. It's a process constantly influenced by our current emotions, our expectations, and even our beliefs. If you were to revisit a cherished childhood memory, you might find yourself subtly altering it to fit a more positive narrative, smoothing over rough edges, emphasizing joyful moments, unconsciously shaping the memory to align with how you want to remember it. Furthermore, the way our brains encode temporal information is surprisingly flexible. Studies using fMRI, functional magnetic resonance imaging, have shown that the same event can be perceived as lasting longer or shorter depending on the emotional content. A happy, exciting event tends to be encoded with a greater degree of detail, creating a richer, more persistent memory, and thus, a feeling of a longer duration. Conversely, a stressful or traumatic experience might be compressed into a more fleeting impression. This isn't a matter of simply remembering more details. It's about the fundamental way our brains represent temporal information. It's worth noting that the human brain doesn't store memories linearly. Instead, they exist in complex networks, and the strength of connections within those networks shifts over time. Memories that are frequently accessed, those that we actively think about or that are triggered by external cues, tend to strengthen, becoming more vivid and persistent. This is known as reconsolidation, a period during which a memory is vulnerable to change and integration with other memories. It's like a sculptor constantly refining a piece, adding detail and altering form based on new insights. The concept of prospective memory, our ability to remember to do things in the future, further illuminates the role of memory in our experience of time. We don't just remember that we need to take the trash out. We remember when we need to do it, a recollection shaped by the context of the present and the anticipation of the future. A vivid reminder, perhaps a strategically placed note, can dramatically alter our perception of the time remaining before an upcoming task, making it feel shorter and prompting quicker action. Moreover, our sense of time is inextricably linked to our anticipation of the future. We constantly build models of what's to come, and these models influence how we interpret the present. If we anticipate a particularly enjoyable event, the present moment might feel drawn out, filled with a sense of eagerness and expectation. Conversely, if we're worried about something ahead, the present can feel constricted, dominated by anxiety and a sense of urgency. This isn't simply about planning. It's about the fundamental way our brains integrate past experience with future expectations. It's also crucial to consider the impact of cultural narratives and shared experiences on our sense of time. Societies often develop symbolic representations of time, calendars, festivals, rituals that shape our understanding of its passage. These shared narratives provide a framework for interpreting our personal experiences and contribute to a collective sense of temporal orientation. Different cultures emphasize different aspects of time, linear versus cyclical, for example, and this inevitably influences how individuals perceive its flow. Ultimately, the feeling of time passing isn't a passive reception of an external phenomenon. It's an active construction, built primarily from the bricks of our memories, each imbued with emotional significance, and constantly reshaped by our present experiences and future expectations. It's a profoundly subjective experience, unique to each individual, and a testament to the remarkable plasticity and dynamism of the human brain. As you drift off to sleep, consider the intricate dance between your memories and your sense of time, a constant, beautiful, and slightly mysterious process. The human experience of time isn't simply a passive recording. It's a remarkably active construction, forged within the intricate workings of our brains. Scientists are increasingly uncovering the specific neural circuits that are responsible for our subjective feeling of temporal passage. Rather than a singular time center, as some early theories suggested, research now points to a distributed network, a vast and dynamic system constantly responding to sensory input, internal states, and cognitive demands. At the heart of this network lies the cerebellum, a structure often associated with motor control, but now recognized as a critical player in time perception. Studies using EEG, electroencephalography, where electrodes are placed on the scalp to measure electrical activity, have repeatedly shown that the cerebellum displays distinct rhythmic patterns, specifically alpha waves, that correlate strongly with the perceived duration of events, particularly durations between 1 and 6 seconds. These aren't simply passive markers. The cerebellum appears to be actively predicting the continuation of a stimulus, adjusting its rhythmic firing to maintain a consistent representation of the elapsed time. Further investigation reveals a key role for the parietal lobe, specifically the intraparietal sulcus IPS. This region is involved in spatial processing, attention, and crucially, the timing of movements. Researchers have demonstrated that the precision with which we can estimate intervals, particularly those involving motor actions, is strongly linked to activity in the IPS. Experiments involving rapid button presses, for example, show a distinct neural signature that evolves over time. Initially, there's a burst of activity in the IPS, followed by a gradually decreasing firing rate as the perceived duration increases. This isn't a simple countdown. It's a dynamic model of time being actively built. Interestingly, The strength of this neural representation is influenced by attention. The more attention we pay to a duration, the more robust and accurate our perception becomes. This suggests a close relationship between focused attention and the brain's internal clock. The basal ganglia, a group of structures deep within the brain involved in movement control, habit formation, and reward processing, also contribute significantly to our sense of time. Recent research utilizing fMRI, functional magnetic resonance imaging, which detects changes in blood flow to measure brain activity, has shown that the basal ganglia are involved in the timing of sequences of actions, like playing a musical piece or performing a motor routine. These sequences aren't just triggered by external cues. The basal ganglia seem to maintain an internal template for the expected order of events, and deviations from this template lead to a sense of temporal distortion. When we're engaged in a familiar and enjoyable activity, our brain's reward centers, including the ventral striatum, are activated, which seems to influence the subjective pace at which we experience time. It's as if the anticipation of reward stretches out time, while boredom compresses it. The prefrontal cortex, responsible for higher-level cognitive functions like planning, decision-making, and working memory, isn't just observing the timing process. It actively shapes our temporal judgments. The anterior cingulate cortex, ACC, for instance, plays a role in conflict monitoring and error detection, and its activity is closely linked to our perception of unexpected temporal shifts. When something disrupts our expectations, like a sudden interruption or a surprise event, the ACC becomes highly engaged, leading to a heightened awareness of temporal distortion. Furthermore, the prefrontal cortex is crucial in maintaining a representation of the present, a constantly updated model of the current moment. And this continuous updating is fundamental to our sense of temporal continuity. Importantly, the brain doesn't process time in isolation. Sensory information from various modalities, vision, hearing, touch, and even smell, all contribute to the construction of our temporal experience. The integration of these sensory inputs occurs primarily in the temporal cortex, a region richly connected to other brain areas involved in time perception. For example, the perception of a longer duration is often accompanied by a greater increase in the number of distinct sensory experiences we have during that time. It's not just about the length of time itself, but also about the richness of the experiences we have within that time frame. Recent advancements in neuroimaging techniques, including simultaneous EEG-fMRI studies, are beginning to reveal the astonishingly complex interplay between these diverse brain regions. These studies demonstrate that time perception isn't governed by a single algorithm, but rather by a massively parallel, distributed network constantly adapting to our immediate environment and internal state. The rhythmic activity observed in the cerebellum, the precise motor timing within the IPS, the habitual sequences within the basal ganglia, and the continuous updating of the present by the prefrontal cortex. All these elements combine to create the remarkably subjective and often surprising experience of time's passage. It's a testament to the brain's extraordinary ability to construct reality, not as a passive observer, but as an active, dynamic participant in the unfolding of experience. The ongoing exploration of the neuroscience of time perception is still uncovering many secrets. Scientists are now investigating the role of the gut-brain axis, suggesting that signals from the digestive system may also influence our internal clock. The field is moving beyond simple linear models of time and towards a more nuanced understanding of how the brain actively shapes our experience of duration, rhythm, and change. The universe isn't a silent, static place. It's a vibrant symphony of energy, constantly vibrating with waves, not just sound waves, but waves of light, radio waves, and countless others. These waves carry information, travel across vast distances, and their behavior is governed by some incredibly fascinating rules. A key piece of this puzzle is something called the Doppler effect. It's a phenomenon that seems simple enough. The pitch of a siren changes as it approaches and moves away from you, but it reveals a profound connection between movement and the very nature of light itself. Consider a race car speeding towards you. As it gets closer, the sound of its engine seems to rise in pitch, doesn't it? This isn't a trick of your ears. It's because the sound waves are being compressed in front of the car. The waves are arriving more frequently, creating a higher perceived frequency and therefore a higher pitch. Now, as the car moves away, the sound waves stretch out and the pitch drops. The same principle applies to light waves. Light, unlike sound, travels at a constant, universal speed, approximately 299,792,458 meters per second. This speed is a fundamental constant of the universe. However, when light interacts with something that's moving, its wavelength, the distance between successive crests of the wave, can change. If a source of light is moving towards an observer, the light waves get compressed, resulting in a shorter wavelength. This shift towards the blue end of the spectrum is known as a blue shift. Conversely, if the source of light is moving away from the observer, the waves stretch out, and the wavelength increases, shifting the light towards the red end of the spectrum. This is a redshift. This isn't just about sound or color. It's about the very fabric of space-time. Einstein's theory of special relativity demonstrated that space and time are intertwined, and that measurements of time and distance are relative to the observer's motion. The Doppler effect with light provides a powerful, measurable way to detect and quantify this relative motion. Scientists use it to study everything from the movement of stars and galaxies to the speed of the solar wind. The most dramatic demonstration of this effect occurs with distant galaxies. When we observe the light from these galaxies, we see that their spectral lines, specific wavelengths of light that identify the elements present, are shifted towards the red end of the spectrum. This redshift is incredibly significant. It indicates that these galaxies are moving away from us, and crucially, that the universe itself is expanding. Edwin Hubble's observations in the early 20th century, based on this redshift, led to the formulation of the expanding universe model. But the application of the Doppler effect to time isn't just about measuring galactic distances. It's a surprisingly elegant concept for probing the flow of time itself. Imagine a hypothetical clock that works by bouncing a beam of light between two mirrors. The time it takes for the light to travel between the mirrors represents one tick of the clock. Now, if the clock is moving, the path the light takes changes. Because the speed of light is constant, the time it takes for the light to complete its journey, and therefore the time recorded by the clock, will be different for an observer at rest relative to the clock versus an observer moving relative to it. This difference in time measurement isn't a philosophical debate about whether time flows differently. It's a direct consequence of the relative motion and the constancy of the speed of light. It's similar to the time dilation predicted by special relativity, where time appears to slow down for a moving observer relative to a stationary observer. However, the Doppler effect with light offers a particularly tangible and observable way to quantify this effect. Scientists have conducted experiments using atomic clocks on aircraft to directly measure these time differences. These experiments have provided strong confirmation of the predictions of both special and general relativity. The precision required is astonishing. We're talking about measuring differences in time that are incredibly small, yet measurable with remarkable accuracy. Furthermore, the Doppler effect provides a tool for studying time distortions caused by gravity. General relativity predicts that gravity bends spacetime, and this bending affects the path of light. When light travels near a massive object, like a black hole, its path is distorted, leading to a redshift that's larger than what would be expected based solely on the object's velocity. This allows scientists to map the distribution of mass and energy in the universe and to study the extreme conditions near black holes. The connection between light waves, motion, and time isn't just a scientific curiosity. It's a fundamental aspect of how the universe operates. It's a reminder that our perception of time is inextricably linked to our movement and to the very fabric of space and time itself. As you drift off to sleep tonight, consider the countless light waves traveling through the cosmos, carrying information about the universe's expansion and offering a remarkable window into the intricate relationship between motion and time. The universe, as we understand it, is a grand, bustling dance of energy and matter. Particles are constantly vibrating, rotating, and interacting. For centuries, scientists believed that this motion was always fundamentally chaotic, a perpetual, unending tremor. But a few brilliant minds, driven by a combination of theoretical mathematics and experimental observation, began to suggest something utterly unexpected: that some systems could, under very specific conditions, exist in a state of completely regular, repeating motion, without any external energy input. This idea led to the discovery of time crystals, a truly remarkable new state of matter, a kind of frozen time. The key to understanding time crystals lies in the concept of symmetry breaking. In typical systems, like a vibrating molecule or a spinning top, there's often a rotational or vibrational symmetry. This means that if you rotate or vibrate the system, it will simply repeat the same motion. However, a time crystal disrupts this symmetry. Instead of just oscillating back and forth in a simple way, its constituent parts, often atoms arranged in a specific lattice structure, spontaneously and precisely cycle through their motion at a regular rate, like a tiny internal clock. Crucially, this cycling isn't driven by an external force. It's an inherent property of the system itself. Consider a simple example: a perfectly symmetrical three-dimensional lattice of atoms. If you were to apply a small magnetic field, the atoms would typically precess. They'd rotate around an axis with a specific frequency determined by the field. But in a time crystal, the atoms actually precess without the magnetic field. They oscillate around an axis, not in a random, chaotic way, but with a meticulously timed, repeating pattern. This pattern isn't just a vibration. It's a rotation that cycles infinitely, forever. The discovery of time crystals wasn't a sudden flash of insight. It was built upon decades of theoretical work, primarily by Frank Wilczek. He first proposed the concept of time crystals in 2012, drawing inspiration from the idea of ordinary crystals, which possess a repeating spatial structure. He realized that if you could create a system with a repeating temporal structure, you'd have something equally ordered and fascinating. The initial research focused on exotic atoms like ytterbium, cooled to temperatures just above absolute zero. At these incredibly low temperatures, the atom's quantum mechanical properties become dominant, and they're more susceptible to exhibiting this unusual time-repeating behavior. The fundamental building blocks of a time crystal are often complex molecules, typically made of ytterbium or mercury. These elements are chosen because their electronic energy levels allow for the creation of the necessary conditions for sustained, repeating cycles. The precise arrangement of these atoms is paramount. The crystal's structure needs to be carefully engineered to facilitate the time-repeating motion. It's like building a musical instrument. The shape and material of the instrument determine the sound it produces. What makes this so strange is that the system appears to be measuring time itself. It's not just repeating a motion, it's doing so at a precise, unwavering rate, independent of any external clock. This suggests that time crystals aren't just passively repeating their motion, they're actively maintaining their temporal order. This has led to profound questions about the very nature of time. Scientists are now exploring different ways to create and control time crystals. One approach involves trapping ions, electrically charged atoms, in electromagnetic fields. By carefully shaping these fields, they can induce the ions to precess at specific frequencies, creating the repeating time-like behavior. Another avenue of research involves complex molecular structures, where the interactions between atoms can be manipulated to stabilize the time crystal state. The potential applications of time crystals are still largely theoretical, but they're incredibly exciting. Because they maintain their temporal order without consuming energy, they could, in principle, be used to build extremely precise clocks, far surpassing the accuracy of current atomic clocks. Furthermore, the ability to manipulate and control repeating cycles at the quantum level opens doors to new technologies in areas like quantum computing and quantum communication. Importantly, time crystals aren't frozen in a completely static state. While they maintain their temporal order, they're not entirely passive. They can interact with their environment, and external influences can subtly affect their cycling rate. However, even with these interactions, the core time-repeating behavior persists, a testament to the system's inherent order. The study of time crystals is pushing the boundaries of our understanding of the universe. They represent a shift in perspective, moving from thinking of time as a linear progression to considering it as a more fundamental, measurable quantity. These bizarre and beautiful systems offer a unique window into the deepest mysteries of time and the very fabric of reality. As research continues, we can expect even more surprising discoveries and a deeper appreciation for the astonishing possibilities hidden within the quantum world. Ultimately, time crystals demonstrate that order and repetition can exist in a way that transcends our everyday experience, and that the universe may hold surprises, yet unimagined. The universe is vast, staggeringly so. We've spent decades, centuries even, peering out into the darkness, driven by a fundamental question: are we alone? The search for extraterrestrial life isn't just a romantic notion of encountering friendly aliens. It's a deeply rooted investigation into the nature of existence itself. This pursuit leads us directly into the perplexing realm of the Fermi paradox. It's a name that rolls off the tongue like a quiet mystery, and it's a puzzle that has haunted scientists and philosophers alike. The paradox, simply stated, is this: given the immense age of the universe, the sheer number of stars, likely countless planets orbiting them, and the high probability of some planets supporting life, why haven't we detected any definitive evidence of extraterrestrial civilizations? Why is there no radio signal, no megastructure visible across interstellar distances, no sign of their presence at all? The argument for a great filter emerges from this silence. This isn't necessarily a malicious entity, but rather a significant barrier, a hurdle that prevents most, if not all, life from progressing to an advanced, spacefaring stage. Perhaps it's something intrinsic to the development of complex life, something incredibly difficult to overcome. Maybe it's the emergence of intelligence itself, a statistically rare event. Or perhaps it's a catastrophic event, a self-inflicted disaster, or a natural phenomenon that wipes out civilizations before they reach a certain technological level. We don't know what this filter is, and that uncertainty fuels much of the debate. But the silence isn't just a question of probability. It's intertwined with our understanding of time, specifically with the concept of the arrow of time. The arrow of time describes the fundamental asymmetry of time. It dictates that time flows in one direction, from past to future, and not the other. This isn't just an observation. It's a deeply ingrained property of the universe, reflected in countless physical laws. For instance, entropy, the measure of disorder, always increases over time. A broken vase doesn't spontaneously reassemble itself. Heat flows from a hot object to a cold one, not the other way around. The fundamental laws of physics are largely time-symmetric, meaning they work equally well whether time is running forward or backward. However, the universe itself undeniably progresses in one direction, governed by this increase in entropy. Now, consider the implications for the longevity of civilizations. A civilization, even a technologically advanced one, must expend energy to maintain order, to combat entropy. Building a starship, constructing a planetary defense system, sustaining a large population, all of these require immense energy input. Maintaining that order, preventing the inevitable decay and disorganization, becomes increasingly difficult over vast spans of time. If a civilization has a limited lifespan, perhaps constrained by its ability to manage entropy, then its presence might be fleeting, detectable only during a brief window of time before it collapses. Furthermore, the rate at which entropy increases could be a limiting factor. If a civilization is building towards interstellar travel, constructing massive structures, they are, by definition, increasing entropy. This suggests a timeline, a critical period, within which they would need to achieve a certain level of technological advancement before the universe itself becomes too chaotic to support such endeavors. This echoes the idea of a cosmic deadline. The Fermi paradox isn't simply about finding aliens. It's about understanding the constraints on existence itself. The universe isn't a static, unchanging backdrop for life to flourish indefinitely. It's a dynamic system governed by fundamental physical laws, laws that dictate the direction of time and the relentless march of entropy. This inherent directionality introduces a potential limit on the duration of any given civilization. Another, somewhat unsettling, possibility arises from the idea of tired light. This hypothesis, largely dismissed but worth considering, proposes that photons, particles of light, lose energy as they travel through space, slowing down and eventually ceasing to propagate. If true, this would dramatically affect the distances light could travel and consequently the observable universe. It would shrink the window of opportunity for civilizations to communicate across vast interstellar distances, as the signals we might be receiving could be distorted and weakened by this effect. The absence of detectable signals doesn't necessarily mean intelligent life doesn't exist. It could mean they're using communication methods we don't understand, technologies beyond our current comprehension. Or, as the Fermi paradox suggests, they might have already perished, lost to the relentless tide of time and the universal tendency towards disorder. It's also worth pondering the possibility that our own perspective is fundamentally flawed. We're searching for signals from civilizations that might operate on timescales vastly different from our own. Their technologies, their motivations, their very understanding of time and space might be so alien that we simply aren't looking in the right way. Perhaps they've transcended the limitations of physical communication, existing in a realm beyond our current sensory capabilities. The Fermi paradox, therefore, isn't just a question for astronomers and physicists. It's a profound philosophical inquiry into the nature of existence, the limits of technology, and the ultimate fate of intelligent life in a universe governed by time and entropy. The silence, the void, is a reminder that our place in the cosmos is perhaps more fragile, more contingent than we might initially assume. Ultimately, the continued search for extraterrestrial life is driven by a fundamental human desire to understand our place in the grand scheme of things. It's a quest not just for alien civilizations, but for answers to some of the most fundamental questions about time, existence, and our own potential fate. The universe, as we've explored, isn't a simple, straightforward river flowing in one direction. It's a tapestry woven with complexities, light bending, crystalline structures holding still moments, and the unsettling possibility that our understanding of existence itself might be profoundly incomplete. Let's delve into a particularly intriguing and increasingly discussed concept: the simulation hypothesis. It's a notion that suggests our reality, this very moment we're experiencing, might not be a fundamental, base reality, but rather a sophisticated computer simulation. The core idea originates from philosophical arguments, primarily developed by Nick Bostrom in 2003. Bostrom proposed three possibilities, and he argued that at least one of them must be true. The first is that humanity will go extinct before reaching a technological stage capable of creating such simulations. The second is that even if we could, we wouldn't. Perhaps there would be fundamental ethical constraints preventing us from creating conscious simulations. Finally, and perhaps most captivatingly, he suggested that if civilizations reached a point where they could create highly realistic simulations, they likely would. Given enough time, a vast number of civilizations would almost certainly generate these simulations, creating countless virtual realities. The implications of this scale are staggering. If Bostrom's argument holds, then the number of simulated realities would vastly outnumber the base reality. It's like an infinite regression, an endless series of nested realities. Now, let's consider what that would mean for time. Within a simulation, time doesn't necessarily have to operate in the same way as our perceived experience. The programmers, the creators of the simulation, could manipulate the flow of time just as easily as we manipulate the resolution of a video game. Think about a video game. The game's clock might run at a different rate than real-world time. Perhaps seconds within the game pass by faster or slower than the seconds ticking outside the screen. The game's developers could even introduce time loops, where events repeat endlessly, or time jumps, where entire sections of the game abruptly skip forward. The key difference, however, is that in a sufficiently advanced simulation, the simulated inhabitants would likely be unaware of this manipulation. They would experience time linearly, just as we do, but the underlying structure of time would be controlled by the simulators. It's analogous to how we perceive the smoothness of a moving image. We see a continuous sequence of still frames, but our brains interpret them as motion. Similarly, simulated beings could be entirely unaware of the temporal distortions occurring within their simulated world. But what about the arrow of time, the seemingly irreversible progression from past to future? In our universe, the arrow of time points consistently in one direction, dictated by entropy, the tendency of systems to move from order to disorder. A broken glass doesn't spontaneously reassemble itself. A dropped egg doesn't unscramble. Within a simulation, this fundamental principle could be bypassed. The programmers could, for instance, rewind time, correcting mistakes, or altering events entirely. They could create pockets of reverse time where causality itself is disrupted. The simulation's parameters could dictate the fundamental laws of physics, including those governing time. Perhaps the speed of light wouldn't be a fixed constant, but could be altered on demand, creating relativistic effects within the simulation without requiring the immense energies involved in the real universe. Or, the programmers could introduce new physical constants entirely, simply by changing the rules of the game. Furthermore, the very nature of consciousness within a simulation is a complex question. Would simulated minds be truly conscious, possessing subjective experience, or would they simply be incredibly sophisticated algorithms mimicking consciousness? It's possible that the feeling of consciousness is itself a simulation, a layer of processing within the simulation that creates the illusion of self-awareness. Scientists are beginning to explore the possibility of simulating consciousness itself. Research in artificial intelligence, particularly in areas like recurrent neural networks and generative models, is bringing us closer to creating systems that can exhibit complex behaviors and seemingly learn and adapt in ways that resemble human intelligence. If we succeed in creating truly conscious AI, it would lend further credence to the idea that consciousness itself isn't unique to biological systems, but could be instantiated in a sufficiently complex computational environment, just like a simulation. The simulation hypothesis isn't a scientific theory in the traditional sense. It's more of a philosophical thought experiment. However, it prompts us to question our most basic assumptions about reality. It forces us to consider the possibility that what we perceive as the fundamental laws of the universe might be merely the rules of the game, determined by an external intelligence. The challenges in testing the simulation hypothesis are immense. There's currently no way to definitively prove or disprove it. However, some researchers have proposed potential glitches in reality, anomalies that might indicate the simulation's underlying code. These could manifest as violations of physical laws, sudden shifts in perception, or even seemingly random events that defy explanation. Ultimately, the simulation hypothesis offers a captivating perspective on our existence, a reminder that our universe, and perhaps our very selves, might be far more intricate and surprising than we ever imagined. It encourages us to remain open to new possibilities and to continue exploring the deepest mysteries of time, space, and consciousness. Let's consider the gentle, relentless nature of change that we experience as we live the process we commonly call aging. It's a phenomenon woven deeply into the fabric of our existence, a constant, quiet transformation occurring at the very foundations of our being. The appearance of wrinkles, the gradual loss of muscle mass, the slowing of reflexes, the susceptibility to illness, these aren't random occurrences. They're manifestations of intricate, extraordinarily precise changes within ourselves. At the heart of aging is a complex interplay of cellular mechanisms, primarily driven by a concept known as genomic instability. Our DNA, the blueprint for every single cell in our bodies, is remarkably accurate, but it's also incredibly fragile. Each cell, during its rapid division, a process called mitosis, needs to faithfully duplicate its DNA. This duplication isn't perfect. There's a small but measurable error rate, like a tiny typo creeping into a book as it's copied repeatedly. These errors, called mutations, accumulate over time. Initially, most mutations are harmless, perhaps even beneficial, but as they stack up, they can disrupt the delicate balance of gene expression. Essentially, they can change how our genes behave. These accumulated mutations contribute to a decline in the efficiency of cellular processes. Proteins, the workhorses of the cell, rely on precise sequences of DNA to be produced. With more mutations, the instructions become less clear, leading to the creation of faulty proteins. These malfunctioning proteins can interfere with vital functions, such as repairing damaged DNA, maintaining cell structure, and generating energy. A particularly crucial player in this process is telomeres. Telomeres are protective caps found at the ends of our chromosomes. Think of them like the plastic tips on shoelaces, preventing the DNA strands from fraying. Every time a cell divides, these telomeres shorten slightly. This isn't a problem when the cell is young, but as cells continue to divide over many years, the telomeres gradually become shorter and shorter. Eventually, they become so short that they can no longer adequately protect the chromosome, triggering a cellular program that signals the cell to stop dividing, a process known as cellular senescence. Senescent cells don't necessarily die, but they lose their ability to perform their normal functions, and they can even release inflammatory molecules that contribute to age-related diseases. Beyond telomere shortening and genomic instability, oxidative stress plays a significant role. Our cells generate energy through a process called cellular respiration, and this process produces harmful byproducts called free radicals. These free radicals are unstable molecules that can damage DNA, proteins, and lipids, the fats that make up cell membranes. Antioxidants, present naturally in our bodies and in many foods, help neutralize these free radicals. But as we age, our antioxidant defenses can weaken. Furthermore, the accumulation of misfolded proteins is a critical factor. Proteins, like chains assembled from individual building blocks, can sometimes fold incorrectly. If these misfolded proteins aren't properly recognized and cleared by the cell's quality control mechanisms, a system called autophagy, they can accumulate and disrupt cellular function. A particularly notorious example is the accumulation of amyloid beta protein in the brains of individuals with Alzheimer's disease. The concept of cellular senescence isn't simply a passive process of decline. It's actually an active response by the cell to protect itself from further damage. However, the sheer number of senescent cells accumulating in our bodies, combined with their inflammatory signaling, creates a feedback loop that can exacerbate age-related tissue dysfunction. It's a complex and delicate equilibrium, constantly shifting as cells respond to internal and external stresses. Interestingly, the rate at which these changes occur varies significantly between individuals, influenced by a combination of genetic factors and environmental exposures. Diet, exercise, exposure to toxins, and even our emotional state can all impact the speed at which our cells accumulate damage. Researchers are actively investigating ways to intervene in this process, exploring strategies such as senolytic drugs, medications designed to selectively eliminate senescent cells, and lifestyle interventions aimed at reducing oxidative stress and promoting cellular repair. It's important to recognize that aging isn't a singular, monolithic process. It's a tapestry woven from countless interconnected events, each occurring at different rates and contributing to the overall transformation of our bodies. While the accumulation of damage is undeniable, the study of aging is revealing a surprising degree of plasticity, the ability of cells and tissues to adapt and repair themselves, particularly in younger individuals. Understanding these intricate mechanisms allows us to appreciate the profound beauty and complexity of the biological process that defines our existence, a process that, despite its inevitable aspects of change, is fundamentally about the ongoing, remarkable ability of life to persist. The shimmering expanse of spacetime, a concept we've been exploring, presents a particularly perplexing challenge when considering the possibility of movement through time, not simply traveling along its current flow, but actively altering it. The very idea throws us headlong into what are known as time travel paradoxes, knots in the fabric of reality that seem to demand impossible solutions. These aren't just theoretical puzzles. They represent fundamental questions about causality, the relationship between cause and effect, and the structure of our universe. The most famous of these paradoxes is, without a doubt, the grandfather paradox. It's a deceptively simple thought experiment designed to expose a critical flaw in the notion of unrestricted time travel. Suppose a time traveler journeys back to a point in the past, and for whatever reason, intervenes to prevent their own grandfather from meeting their grandmother. Let's say, perhaps, they accidentally cause a minor accident that leads to the elder man's untimely demise. If the grandfather never lives, then the time traveler's parent is never born. Consequently, the time traveler themselves is never born, creating an immediate contradiction. The act of going back in time to prevent their birth prevents their birth. The core of the paradox lies in the violation of causality. Our understanding of the universe generally assumes that events unfold in a specific sequence, where one event causes another. If you can rewind that sequence and negate the cause, the effect ceases to exist, leading to a logical breakdown. It's a self-annihilating loop. Now, it's crucial to recognize that the grandfather paradox isn't necessarily evidence that time travel is impossible. Rather, it highlights the potential consequences of tampering with the past, suggesting that the universe might possess mechanisms to resist such alterations. However, the linear, cause and effect model of time isn't the only way to conceptualize reality, and various theories offer potential resolutions to the paradox. One prominent concept is the many worlds interpretation of quantum mechanics. This interpretation proposes that every quantum measurement, every event with multiple possible outcomes, doesn't result in a single, defined reality. Instead, it creates a split, branching the universe into separate, parallel realities, each representing a different outcome. Applying this to time travel, the act of a time traveler altering the past wouldn't change their original timeline. Instead, it would create a new, separate timeline, an alternate reality. The time traveler would be creating a new branch of existence. So, if they were to prevent their grandfather's meeting with their grandmother, they wouldn't erase themselves from their original timeline. They would simply be existing in a timeline where they were never born, but their original timeline remains untouched. This avoids the direct contradiction of the grandfather paradox, but it raises new questions about identity and the nature of reality. Furthermore, these alternate timelines aren't necessarily disconnected from the original in any meaningful way. Some theories suggest that these timelines are connected through subtle, perhaps undetectable, interactions. Perhaps the energy involved in creating a new timeline leaves a faint ripple effect that subtly influences events in both the original and the altered realities. This could explain why, in some fictional portrayals of time travel, small changes in the past can have surprisingly large consequences in the future. Those consequences are echoes of the alterations made in a different timeline. Another way to think about it is through the concept of self-healing timelines. Perhaps the universe has a default state that it strives to maintain. Any attempts to significantly alter the past would be met with resistance, with events subtly shifting to restore the original timeline. This resistance might manifest as improbable coincidences, unforeseen obstacles, or even physical alterations designed to steer the time traveler back towards the established course of events. It's akin to a river trying to flow in a straight line, even if someone throws a large rock into it. The study of time travel paradoxes isn't just an abstract intellectual exercise. It's fundamentally tied to our understanding of the laws governing the cosmos. The constraints imposed by these paradoxes, if they exist, would likely be incredibly complex and potentially far beyond our current comprehension. They could involve entirely new physical principles, perhaps related to energy conservation, information theory, or even the very nature of spacetime itself. Moreover, the existence of alternate timelines implies a vast, potentially infinite multiverse. Each decision, each event, branches off into countless possibilities, creating a boundless landscape of realities. This raises profound philosophical questions about free will, determinism, and the meaning of existence. If every possible outcome already exists in some reality, does our individual choice truly matter? The ongoing exploration of time travel paradoxes serves as a powerful reminder that our perception of time as a linear progression is likely a simplification. The universe may be far more intricate and dynamic than we currently realize, and the possibility of manipulating time, while fraught with logical challenges, continues to inspire scientific inquiry and fuel our imaginations. It compels us to confront the deepest questions about our place in the vastness of existence, and to consider the profound implications of a reality that might be far more fluid and interconnected than we ever imagined. The universe, as we perceive it, is fundamentally built on something called space-time. It's not just a backdrop for events. It's an active participant, woven together from three dimensions of space, length, width, and depth, and one dimension of time. Einstein's theory of general relativity revealed that massive objects warp this fabric, creating what we experience as gravity. A bowling ball placed on a stretched rubber sheet causes a dip. A planet orbits a star because it's following the curves created by the star's immense mass. This warping isn't just a theoretical curiosity. It has observable consequences, like the bending of light around massive objects. Now, let's consider what happens when you pack an enormous amount of mass into an incredibly small space. This is the situation within a black hole, the most extreme example of space-time distortion imaginable. Black holes aren't just holes. They're regions where gravity is so intense that nothing, not even light, can escape. The formation of a black hole usually begins with the collapse of a massive star at the end of its life. As the star runs out of fuel, the outward pressure from nuclear fusion ceases and gravity takes over, relentlessly crushing the star inward. As the mass continues to concentrate, the curvature of space-time around the object increases dramatically. It's like cranking up the magnification on that rubber sheet. The dip becomes infinitely deep. This extreme warping isn't just a localized effect. It stretches and distorts space-time across vast distances. We can use mathematical equations, specifically Einstein's field equations, to describe precisely how space-time is affected. These equations predict that the closer you get to a black hole, the more dramatic the distortion becomes. At the very center of a black hole lies what is known as the singularity. This isn't a physical object in the traditional sense. It's a point of infinite density. All the mass of the black hole is compressed into a single point. Our current laws of physics, particularly general relativity, break down at the singularity. The equations produce infinite values, suggesting that our understanding of the universe simply fails to describe what's happening there. It's a place where space and time, as we understand them, cease to have meaning. Consider the effects of time near a black hole. General relativity predicts that time slows down for an observer approaching the event horizon, the boundary beyond which escape is impossible. This isn't a trick of perspective. It's a fundamental consequence of space-time itself being warped. An observer far away from the black hole would see an object falling towards the event horizon as appearing to slow down, its movements becoming increasingly stretched and faint, until it eventually seems to freeze at the edge. Let's explore this effect with a thought experiment. Imagine a spaceship approaching a black hole. From the perspective of an astronaut on the spaceship, time continues to pass normally. They eat, sleep, conduct experiments. Everything seems perfectly normal. However, from the perspective of an observer back on Earth, the astronaut's clock appears to be ticking incredibly slowly. The closer the spaceship gets to the event horizon, the slower time appears to pass for the astronaut relative to Earth. The reason for this is rooted in the fact that the extreme curvature of space-time requires energy to move through time. As an object approaches the event horizon, it has to expend more and more energy to move forward in time, as seen by a distant observer. This means that time effectively dilates or stretches for the object falling into the black hole. Now, let's talk about the potential for time travel, a fascinating, if somewhat unsettling, consequence of these effects. Hypothetically, if an astronaut could survive the tidal forces, the immense difference in gravitational pull across their body, and withstand the radiation near the event horizon, they could, from Earth's perspective, spend a significant amount of time within the black hole before returning. They might emerge having experienced decades, centuries, or even millennia, while only a few years had passed on Earth. However, this scenario is fraught with problems. The tidal forces would almost certainly rip the spaceship and the astronaut apart. The intense radiation near the event horizon would be lethal, and critically, the singularity itself represents a complete breakdown of space-time, meaning any attempt to return would likely be impossible. The mathematics suggest that time dilation becomes infinitely large at the singularity. This doesn't mean that time stops in the absolute sense, but that the concept of time as we perceive it loses all meaning. The equations simply don't apply. It's a region where our understanding of the universe falls apart. Scientists are continually studying black holes through observation, primarily by detecting gravitational waves produced by black hole mergers, to refine our understanding of these enigmatic objects. These observations offer tantalizing glimpses into the behavior of spacetime in extreme conditions. The more we learn about black holes, the more we appreciate the profound and interconnected nature of space and time. Black holes aren't just cosmic vacuum cleaners. They are laboratories for testing the limits of our understanding of the universe, and a stark reminder of the incredible power and strangeness of gravity's influence on space-time. They represent the most extreme manifestation of Einstein's theory, challenging our intuition about the fundamental nature of reality. The universe, in its grand choreography, seems to operate on a rhythm, a fundamental beat we call time. But how do we actually know time is passing? How do we measure something so intrinsically linked to change and decay? For centuries, humanity relied on the sun, the moon, and the stars, a wonderfully intuitive system, certainly, but one riddled with inaccuracies. The changing length of a shadow cast by a stick, meticulously observed over many hours, allowed ancient civilizations to track the sun's journey, giving rise to the concept of days. The position of the stars, carefully noted and charted, revealed the passage of seasons and years. These methods were remarkable for their time, providing a framework for calendars and a sense of the world's relentless flow. However, they were dependent on external factors. The sun's position was affected by clouds, the moon's phases shifted subtly, and the stars themselves weren't perfectly constant. The need for something more precise, something intrinsically tied to the very nature of the universe, spurred a revolution in our understanding and measurement of time. This revolution began with the rise of incredibly sensitive instruments, specifically atomic clocks. These aren't the ticking clocks you might be familiar with. They are sophisticated devices that exploit the incredibly regular vibrations of atoms to measure time with unprecedented accuracy. The key lies in a phenomenon called atomic resonance. Every atom, regardless of its size or composition, possesses a natural frequency at which it vibrates. This frequency is determined by the energy levels of its electrons. Cesium, a silvery gold metal, proved to be particularly useful. In 1955, scientists at the United States Naval Laboratory successfully built the first atomic clock, utilizing a sample of cesium-133. This clock wasn't measuring time directly. Rather, it was measuring the frequency of radiation emitted by cesium atoms as they transitioned between energy levels. Specifically, cesium-133 atoms absorb microwave radiation at very specific, extremely narrow frequencies. When these atoms are stimulated with the correct frequency, they jump to a higher energy level, emitting a photon of radiation at that same, precisely defined frequency. This emitted radiation, a beam of microwaves, is then meticulously measured. The beauty of this system is that the energy levels of cesium-133 are incredibly stable. The electrons are held in place by the strong electromagnetic force of the nucleus, making them remarkably resistant to external influences. Changes in temperature, pressure, or even the gravitational field have a negligible effect on their energy levels. Consequently, the frequency of the emitted radiation remains astonishingly constant. This consistency is what allows atomic clocks to tick with extraordinary precision, far more accurate than any pendulum or spring-driven clock. Modern atomic clocks utilize different elements, including rubidium and hydrogen, each with its own unique atomic resonance frequency. However, cesium remains the gold standard, often serving as the basis for defining the second, the fundamental unit of time in the International System of Units, SI. 1 second is defined as the duration of 9,192,630,1,770 periods of radiation emitted during the transition between two specific energy levels of the cesium-133 atom. This definition ensures that the second remains independent of any physical artifact. It's based solely on the properties of the atom itself. The impact of atomic clocks on our understanding of time is profound. Before their widespread use, timekeeping was subject to considerable uncertainty. The Earth's rotation isn't perfectly constant. It's gradually slowing down due to tidal forces exerted by the moon. This variation, though tiny, would accumulate over time, leading to discrepancies between the time shown on clocks and the actual passage of time. Atomic clocks, operating independently of these terrestrial effects, have allowed scientists to precisely track these variations and refine our knowledge of the Earth's rotation. Furthermore, the measurements made by atomic clocks are critical for a range of scientific and technological applications. They are essential for global positioning system, GPS, satellites, which rely on incredibly accurate time signals to determine their position with astonishing precision. The satellites constantly transmit time information, and your GPS receiver uses this data, combined with signals from multiple satellites, to calculate your location on Earth. Atomic clocks are also used in fundamental physics research. They're employed in experiments testing Einstein's theory of relativity, particularly the effects of time dilation. the phenomenon where time passes differently for observers in different frames of reference. By comparing the time measured by atomic clocks on airplanes traveling at high speeds with the time measured by clocks on the ground, scientists have directly verified the predictions of relativity. The tiny differences in time measured demonstrate that time is not absolute, but rather is relative to the observer's motion and the strength of the gravitational field. The continued development of atomic clocks is pushing the boundaries of precision even further. Scientists are working on creating optical atomic clocks, which utilize the transitions of atoms in the visible light spectrum. These clocks have the potential to be significantly more accurate than current atomic clocks, opening up new possibilities for scientific research and technological applications. As we continue to delve into the intricacies of the universe, the accurate measurement of time, facilitated by these remarkable instruments, will undoubtedly play a crucial role in our understanding of its fundamental nature, a nature that is, itself, constantly in motion and exquisitely sensitive to the smallest vibrations within the fabric of space-time. The ticking of an atomic clock, a subtle yet powerful reminder of the universe's ongoing dance. The shimmering distortion of space-time, once a stark visualization of black holes, began to subtly shift its focus. It wasn't a return to the mechanics of gravitational lensing or the rapid compression of matter. Instead, the visualizations coalesced around a radically different understanding of time itself, the notion of the eternal now. This wasn't a rejection of time's progression, but a profound suggestion that, at its deepest level, time as we experience it is an illusion, a construct of our perception. The idea has roots in ancient philosophies, particularly in Hinduism and Buddhism, but modern physics, combined with these traditions, offers a compelling argument. Consider the experience of a vibrant sunset. You see the colors deepen, the light fades, and you perceive a change happening before your eyes. You mark the moment as evening and register it as a passage of time. But what if that entire sequence, the rising of the sun, the spread of colors, the gradual darkening of the sky, already exists? What if, from a sufficiently detached perspective, there isn't a before and an after, only a single, unified event unfolding without beginning or end? The eternal now proposes that all moments in time, past, present, and future, are equally real and coexist simultaneously. This isn't about temporal ignorance. It's a radical claim about the nature of reality. It suggests that our consciousness, with its inherent need for sequence and narrative, is the reason we feel time flowing. We are like radio receivers tuned to a specific frequency, interpreting the signals as a linear stream. But the signal itself, the universe, isn't inherently linear. It's an infinitely complex tapestry of interwoven events, all existing within the same now. The sensation of movement arises from our subjective experience, our cognitive processing of information. The implications are staggering. If all moments are equally real, then the concept of causality, the idea that one event causes another, becomes significantly more complicated. It's not necessarily a strict, unidirectional flow. Interactions could occur across what we perceive as temporal boundaries. This doesn't imply we can break the laws of physics. The universe remains governed by its fundamental rules, but it challenges our intuitive understanding of how those rules operate. Philosophers have long grappled with the problem of change. How can something change if everything exists simultaneously? The eternal now offers a solution. Change isn't a physical transformation, but a shift in our perspective. Just as a painter can create different images on a canvas by altering their viewpoint, the universe constantly reveals new aspects of itself to a conscious observer. Each new observation, each new piece of information received, brings a different facet of that eternal reality into focus. Furthermore, this concept provides a potential explanation for certain puzzling aspects of quantum mechanics. The observer effect, for example. The act of observing a quantum system seems to influence its behavior, can be understood differently. If all moments exist simultaneously, then the act of observation isn't interfering with a predetermined state, but rather selecting a particular slice of the eternal reality for our consciousness to experience. It's like choosing a single frame from an infinitely long film. The challenge, of course, is how to reconcile this with our everyday experience. We are overwhelmingly aware of a forward-moving arrow of time, influenced by entropy, the tendency of systems to move from order to disorder. This is undeniably a powerful force, driving the evolution of the universe and shaping our individual lives. However, the eternal now suggests that this arrow isn't a fundamental property of the universe, but a product of our consciousness's limited processing capabilities. Consider the measurement of time itself, as explored in a previous part. Atomic clocks, with their incredible precision, are effectively mapping the subtle fluctuations in the eternal now. They're not creating time, but rather providing a highly detailed record of its inherent complexity. The ticking of a clock, the progression of days, the aging of a tree, these are all experienced through the lens of our linear perception, projecting a sense of temporal flow onto a fundamentally timeless reality. It's important to remember that the eternal now isn't a denial of scientific understanding. It's a metaphysical interpretation, an attempt to grapple with the deepest questions about the nature of existence. It suggests a level of reality beyond our immediate grasp, a reality that we can only partially perceive through the filters of our consciousness. The universe, in this view, is not a story to be told, but a song to be listened to, a vast, infinitely complex melody that exists fully and simultaneously. The more we learn about the intricate workings of the cosmos, the more we realize that the questions we ask about time may be fundamentally misguided, rooted in a limited perspective that fails to appreciate the full, eternal richness of existence. The universe doesn't simply tick onward, a steady drumbeat against the void. Our perception of time, so stubbornly linear to our minds, is profoundly shaped by patterns, by sequences that resonate within us. Consider music, a human invention, of course, yet one that reveals a surprisingly deep connection to the very fabric of temporal experience. The core of music's influence lies in rhythm, a repeating series of durations, variations in length that create a sense of order, anticipation, and resolution. A simple pulse, like a heartbeat, is an incredibly basic rhythmic structure, and it's been observed that even infants respond to rhythmic stimuli, indicating an innate understanding of this fundamental temporal element. The brain doesn't just hear a rhythm, it begins to model it, predicting the next beat, anticipating the arrival of a change in sound. This predictive processing is a key mechanism for our experience of time. When things are predictable, time seems to flow smoothly, almost unnoticed. Conversely, when rhythms become irregular, unpredictable, or chaotic, our brains struggle to make those predictions, and time often feels stretched, elongated, even frightening. Beyond the individual beat, harmony introduces another critical layer to this temporal framework. Harmony isn't merely about pleasant sounds. It's about the relationships between pitches and their durations. Intervals, the distances between notes, create a sense of stability or tension, and their resolution, the movement of these intervals towards a more consonant sound, produces a feeling of release, a completion of a temporal phrase. Just as a musical phrase has a beginning, a middle, and an end, so too does our experience of time when listening to music. The careful manipulation of harmony, the use of dissonances followed by resolutions, directly affects our sense of temporal flow. Complex harmonies, densely packed with overlapping rhythmic and tonal elements, can create a powerful illusion of stretched time, demanding our full attention and demanding that our brains work harder to process the intricate temporal relationships. Simpler harmonies, conversely, can allow our minds to relax, to let go of the need for constant prediction, and this can accelerate our perceived experience of time. The study of music has yielded fascinating insights into how our brains actually represent time. Experiments using music as a stimulus have shown that the same brain regions involved in processing auditory information are also activated when we experience time passing. Specifically, the auditory cortex and the cerebellum. This suggests a fundamental overlap in the neural circuits responsible for both hearing and perceiving time. Furthermore, research into musical training has revealed a remarkable correlation between musical expertise and an enhanced sense of temporal accuracy. Musicians, particularly instrumentalists, appear to have a heightened ability to perceive subtle variations in time, allowing them to synchronize their movements with complex rhythms with incredible precision. This is likely due to the extensive training required to master musical instruments, which forces individuals to develop a deeply ingrained understanding of temporal relationships. But it's not just about individual notes and rhythms. The overall structure of a musical piece, its form, plays a significant role in shaping our temporal gestalt. A sonata, for example, typically follows a defined structure with distinct movements, each of which has its own tempo, mood, and harmonic progression. This formal architecture provides a framework for our experience of time, guiding our expectations and influencing our perception of duration. The journey through the movements of a sonata creates a sense of narrative, a story told through sound, and this narrative structure is inextricably linked to our temporal experience. The concept of a temporal gestalt, a unified, holistic experience of time, emerges most powerfully through music. It's the feeling of being completely immersed in a piece of music, losing track of time, feeling as though the music is unfolding at its own pace, independent of our conscious awareness. This isn't simply about enjoying a beautiful melody. It's about a deeper, more profound connection to the very nature of time itself. The brain actively constructs this gestalt by integrating sensory information, the sound of the music, the emotional impact of the melody, the physical sensation of movement, into a cohesive temporal representation. The more engaged and attentive we are to the music, the stronger this gestalt becomes. Consider improvisation, particularly in jazz. A skilled improviser doesn't simply play notes, they sculpt time, weaving intricate patterns of sound that respond in real time to the music around them. They aren't just reacting to previous notes, they're anticipating the next, creating a constantly evolving temporal landscape. The ability to respond so fluidly to the ongoing musical conversation suggests a level of temporal awareness that goes far beyond mere listening. It's a profound engagement with the underlying rhythms and structures of time. The ability to feel the music's pulse and respond to it in real time implies a deep understanding of how time is constructed and experienced. This interplay between listener and musician, a constant exchange of temporal information, creates a unique and powerful aesthetic experience. Ultimately, the study of music in time reveals that our perception of time is not a passive, objective measure, but rather an actively constructed experience, shaped by our sensory input, our cognitive processes, and our emotional state. The rhythmic patterns, harmonic relationships, and formal structures inherent in music provide a powerful framework for this construction, allowing us to not just hear time, but to feel it in a profoundly meaningful way. It's a reminder that even within the seemingly simple act of listening to music, we are engaging with one of the most fundamental and elusive aspects of reality. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the curious mystery of where time goes when it passes. Let your thoughts drift now, calm and unhurried like clouds across the evening sky. Allow your mind to settle gently until sleep finds you.